out. Maybe it's that.
Yeah, this is it. Okay, you started. Perfect.
Great.
Now it's done. Now it's done.
Yeah. Thanks for having me here and being so patient with.
Sorry about the problem. Something changed in my interface in Zoom. I don't know why. Maybe they upgraded it. Okay, let's start our seminar. It's my big pleasure to introduce Christian Liedtke from München. And Christian will tell us why every K3 surface has infinitely many rational curves.
Yeah, thank you so much for having me and being patient. So the title of my talk is Rational Curve on K3 Surfaces. And I'll be talking about two articles joined with Xi Chen from Alberta, with Frank Gunelas, who used to be or is currently still in Munich, but is going to be in Göttingen soon, and myself, who's going to stay maybe forever here in Munich. It's two archive preprints, curves on K3 surfaces and rational curves on lattice polarized K3 surfaces. And let me start with a little bit of background. Oh no, first with the table of contents. So I'll be talking a little bit about why we should be interested in rational curves and algebraic varieties at all, and why this is interesting. Then I'll be switching to rational curves on K3 surfaces. It is already a non-trivial result that there is at least one curve. It's not due to myself. There are some special cases known. The very general case is known. And then sort of we will get the result, unfortunately, not by one nice technique, but it's more by combining several cases. So let me say a couple of words about rational curves and algebraic varieties and why we care. So let X be a variety, and for the purposes of my talk, I'll be smooth and proper even over the complex numbers. If you're interested, I can say a couple of words about characteristic P at some point, but this is already going to be slightly technical, and let's not make it more complicated. So a rational curve, by abuse of notation, will be either a non-constant morphism from P1 to some variety, or the reduced image of such a morphism. So the image could be a P1, but it could also be, for example, in the plane, a nodal rational curve, or can have more singularities. What is important that whenever I would say rational curve in the talk, I will mean an integral curve, reduced and irreducible. So this is a rational curve. And so to start with the obvious and easy cases, what is a rational curve in dimension 1? So you have a curve of genus G, and it follows essentially from Riemann-Horwitz that if you have a non-constant morphism from P1 to a curve, then it's automatically, because we're in dimension 1, it's surjective. And so this can happen if and only if the curve itself has genus 0. So in particular, we're over the complex numbers if it's P1 itself. Okay, this is maybe not so interesting, but something maybe sort of as a warm-up. Now, the next case is if you have a smooth and complex variety proper such that the anti-canonical bundle is ample, then it is known by work of Kolam, Ya, Oka, and Mori that it's rationally connected. That is, whenever you have two general points on this Fano variety, then you can connect it by a rational curve. In particular, there are not only plenty of rational curves on a Fano variety, but it's literally covered, and you have loads and loads of freedom. You can move them around, you can push them around. And I mean, so in the Fano case, there is loads and loads of rational curves, and this is made precise by this, what we say when we say it's rationally connected. On the other hand, if you have an abelian variety, so you have a morphism from P1 to an abelian variety, then just by the universal properties of the Albanese map, this has to factor through the Albanese map of the Albanese variety of P1, which is a point. So every map from P1 to an abelian variety must be constant. In particular, there are no rational curves on abelian varieties. So this is, so Fano a lot, abelian varieties no. And then there's the conjecture of Serge-Lang, which says that if you have a smooth and complex variety of general type, then he says, well, he conjectured that all rational curves all should be contained in some proper and closed subset. Of course, if you, I mean, it's easy to see that there can be rational curves. Just, I mean, especially if you're in high dimensions, it's possible, for example, already on hypersurfaces of large degree in projective n space in large dimension, you can find, for example, a P2 contained in that variety. It may have codimension 47, but then it will have loads and loads of rational curves in it. But so there can be infinitely many, but conjecturally they should be all contained in a proper closed subset. And in particular, in dimension 2, it means that a surface of general type contains only finitely many rational curves. Of course, these conjectures are closely related to questions of hyperbolicity. And so, for example, but this is known, as far as I know, only in very, very few cases. But this is the general picture. Varieties of general type should contain very few rational curves. Fano varieties, on the other extreme, loads. And so the intermediate case, for example, if kx is trivial, we've seen already with abelian varieties that there are none. So it's an interesting question what one can say about K-free surfaces. K-free surfaces, so to recall, so a K-free surface for me will be a smooth and projective surface over the complex numbers with trivial canonical class. And I like Miles Reed's definition, who says, and plus a condition that prevents it from being an abelian variety. So for example, H1 of OX being 0. The prototypical example, and already everything I'll be saying today will be non-trivial in this prototypical example, is if you take a hypersurface of degree 4 in P3, or a complete intersection of a quadric and a cubic in P4, or a complete intersection of 3 quadrics in P5. But there are many more. These are sort of borderline between Fano and general type. We have already seen that for the other class in dimension 2, namely abelian varieties, there are no rational curves. So the interesting question is, what about K-frees? Now for K-frees, there is a remarkable result. It's a little bit difficult to trace to whom it's due, which says that if you have a K-free surface and you have a non-trivial and effective invertible sheaf, so for example, take a sufficiently ample polarization, then there is a result which you can find in an article by Mori and Mukai, and then they attribute it to Bogomolov and Mumford and others, and then they say it's probably, I mean, it will be published at some point, so and it never was, so it is, the only reference is Mori Mukai from 1983, which says that if you have a non-trivial and effective invertible sheaf, then you can always find a section of this line bundle which is supported on rational curves. So these ni's, these coefficients that you see here, could be arbitrarily large, but there's nothing really you can say. I mean, how do you prove such a result? What they do is they look at the K3, they go to the moduli space, they deform it to a nearby surface, then they find a Kummer surface nearby. So it's a deformation degeneration argument, and you'd completely lose control over things like these components there. The Ni are non-negative, of course. And the corollary is, because, I mean, for me, I mean, K3s are algebraic, they're projective. You can always find effective line bundles on them. So at least we have one rational curve. This is already very much different for the situation, say, for abelian varieties, where we've seen there is no rational curves. So a natural question is, well, how many rational curves do we have on a K-free surface? And there is a folklore conjecture, sometimes, well, attributed to people, I mean, sometimes Bogomolov and others, that says that every K-free surface contains infinitely many rational curves. So what we have since the 80s, we have one, and the conjecture is there are infinitely many of them. And today's topic will be the following theorem that this is true. And I mean, I should be honest and modest enough to say that somehow with these two articles I was mentioning in the beginning, together with Shi Chen and Frank Gonelas, we only established the missing cases. Why is this a remarkable result? Or why should you actually believe in this conjecture? This, I should say, you see, if you look at, for example, Collar's book on rational curves and algebraic varieties, how do you prove that you can cover a final variety with rational curves? Well, the idea is to produce a very free rational curve. So you have to produce one very, very, very good rational curve, and then it starts moving over the whole final variety. So in some sense, it's, well, no disrespect, but the question is you have to construct one very good and very nice rational curve. The problem with this conjecture is that rational curves, at least over the complex numbers on K-free surfaces, cannot move. So every rational curve is rigid. So if there are infinitely many of them, there must be for every single rational curve, there must be a different reason why it is there. So I should also say that this makes this a very weird conjecture, because you say, well, there are infinitely many, and they will be Zariski dense because it's a surface, but somehow there is a different reason for every rational curve. There is no, at least we will see, in general, there is no way that even if you have 2,000 rational curves, to find even one more. So,
and excuse me, what can be said about degree of this curve? So, for example, with respect to some polarization,
this will go to infinity.
Okay.
This will go to infinity. Yes. I will also give another thing at the very end. Yes. Yeah. Because I think if you can only have a finite number of bounded degree. This is sort of a Hilbert scheme argument, because if it was infinite of bounded degree, then they would have to lie. Then you would have, every fixed linear system can only contain a finite number of rational curves. And so thank you for this question, because it also tells you again that even if you've produced some rational curves, the question is, how can you find more? So how do you approach such a conjecture, or why do you want to believe in it? So let me start with important special cases. This is work of Bogomolov and Chinkel from 2000. And it says a K-free surface contains infinitely many rational curves if the automorphism group is infinite. We already have one, and you only have to prove that if you restrict if you have an infinite automorphism group, it is at least plausible that using the automorphism group, you can move the rational curve sort of around. So this is a statement on stabilizers, and that the stabilizer group of a rational curve can only be finite. So if the automorphism group is infinite, then we have infinitely many rational curves. Moreover, you can also show that if the K-free surface admits a genus 1 fibration, then there are infinitely many rational curves. This is a very, very beautiful argument where they produce a rational curve, which is a multisection of the fibration, which is non-torsion with respect to the group structure of the Jacobian. So basically, if you have one of these rational multisections, then you can use the group structure that is lurking around in the relative group structure, which is lurking around, or the torsor structure, to push around this rational curve. In particular, you can show that if you have a K-free surface of pK rank at least 5, then it automatically contains a genus 1 pencil. Therefore, it has infinitely many rational curves. And then I should also mention that if the cone of effective curves is non-polyhedral, then you can choose a limit going to some boundary point which doesn't lie in the rational span of the previous ones, of the previous classes, and go to the boundary, and then by Bogomolov, Mukai, Mori, and Mumford, you can produce rational curves that must be distinct. So the upshot of this result of Bogomolov and Schinkel is that for special K-free surfaces, this is true. Just to give you an idea, for example, inside the moduli space of all K-frees, so the algebraic ones form a 19-dimensional family. The locus where you have a genus 1 fibration is codimension 1. So you already have quite a number of divisors inside moduli spaces where the conjecture is true. And then, yeah. So in important special cases, it is true. Now, it is also true by work of Shi Chen in the very general case. Why is it true in the very general case? You look at the moduli space of polarized K-free. So you fix a line bundle ample such of self-intersection number 2D. And then there's a 19-dimensional moduli space. And then what Shi Chen does is he degenerates the K-free to a union of rational surfaces. On rational surfaces, it is very easy to produce rational curves, but it is not easy to move them back into the moduli space. But he achieved this, and then so he can produce quite a number of rational curves on K-free surfaces in this moduli space. So just to get you an idea what the problem is. The problem is, suppose now you have a line bundle of self-intersection number 2D, and you've produced, on the boundary, you produced rational curves in L, 2L, 3L, in the linear system 4L, in the linear system 5L, and you transport them back to the interior of the moduli space. Then what can happen is that at points, it could happen that the rational curves, they deform nicely, that at some point, they start to collapse to the same rational curve. So you have like an integral rational curve in 5L, and then you deform it a little bit, and then at some point, it becomes reducible, like 2 rational curves plus 3 rational curves. So even if you produce at the boundary of the moduli space infinitely many rational curves, they might start collapsing. I mean, nobody believed that, but it could happen. So if you remove infinitely many divisors where this collapsing behavior can happen, then the result and upshot is that on a very general surface that is in this moduli space removed a countable union of divisors, a K-free surface does have infinitely many rational curves. And so from this moment on, it became clearer and clearer that this conjecture is going to be very complicated. Why? We have the very general case. We know it's true in special cases. So if the conjecture is not true, how can you possibly ever find a counterexample if you know that these extreme cases are okay? So the next breakthrough was work of Bogomolov, Hassett, Schinkel, and then with a substantial refinement by Jun Li and myself, where we showed that a K-free surface with odd Picard rank has infinitely many rational curves. So in particular, Picard rank 1, which is the very general case in the moduli space. I will comment on how to prove that a little bit later when I'll be discussing regeneration. And so we now have, until last year, the situation was we had Shi Chen's result, which says it's true in the very general case. We have it's true for many, many special cases, and it's true in the odd rank case. And so the question is, what is missing? What is missing is, as I said, from Picard rank 5 on, we are elliptic, so this is covered. So you can do an analysis. which was done, I think, already by Bogomolov, Chinkel, and I think Winberg, who showed that it's open for K-frees of pK rank 2. 3 is again covered by my result with Jin Li. And in case 4, in pK rank 4, there is only a finite number of lattices where we know that the corresponding K-frees have finite automorphism groups and are non-elliptic. But so these were the open cases. So the question is, how can you deal with them? They are not very general and they are not very special either. And to explain how to deal with these remaining cases, I should say that we introduced, now coming back to work with Shi Chen and Frank Cornelis, 2 new techniques. One is called regeneration, which is an improvement on ideas of the article that I have with Jin Li. This is interesting because it gives a sort of cleaner and easier, slightly easier proof for odd pK rank, and a new ingredient which is called the marked point trick. I will comment on what that is. So let me firstly explain again what the problem is. I mean, how do you prove results like that? Of course, in the end, it's all about degeneration and deformation. So if you have a family of algebraic K-free surfaces over a pointed disk or the spectrum of C double bracket, oh, one of the brackets is missing, and you have a rational curve on the generic fiber of that family, and you specialize it to the special fiber, then one problem you're usually facing is that this rational curve specializes to a union of rational curves. Of course, you cannot, if you specialize a rational curve, there cannot be an elliptic curve, but it could break up. And this is something which you usually have very little control. And then the other thing is you can try to start from this special fiber and go to the generic fiber. And then there are results due to, it's called the Semi-Regularity Map. These are results due to Rahn, Bloch, and Voisin, which say that if you have, say, an integral curve of genus G on the special fiber, say a rational curve, and suppose the line bundle extends, OX of C. So the line bundle O of this curve extends to the whole family, then what is remarkable is then, of course, it's not difficult to see in that situation that you can extend the section to something, but you can deform it as a curve of genus G. Why is this remarkable? We're usually dealing with singular curves. So even in genus 0, you have a rational curve in the special fiber, which has arithmetic genus 2000. So what you would expect if you just lift the section of the defining C to the generic fiber, if you do this just randomly, what will happen is usually that you will smoothen out some of the singularities, and you will get, for example, a curve which still has some singularities, but the geometric genus, so the genus after normalization, will have gone up. So it's no longer a rational curve. However, this is a particularity of K-free surfaces. If you have a curve of genus G in the special fiber, you can deform it to the generic fiber, keeping the genus. And this now leads me to a new, to the first new technique which we've been introducing. So this is a generalization of deformation. Namely, we want to drop the assumption that OX of C extends to the generic fiber. So we want to have a technique that allows us to deform to deform a curve of genus G, for example, a rational curve, to the generic fiber, even if the line bundle does not extend. So usually you would say, no, this is, no way, how can that be? There is a way. The statement goes as follows. Suppose you have an integral curve of genus G on the special fiber, then we claim that we can find an integral curve of genus G on the generic fiber. Well, such that the specialization is the given curve plus possibly a bunch of rational curves. So, so this is the advantage of this type of result is that, I mean, if you work in the moduli space, it means that you can push around a curve of genus G, for example, a curve of genus 0, much easier, because you don't have to assume the line bundle extends. The price you have to pay is that you can do this, that you have to add possibly rational curves. So if you specialize back, you get the original thing plus rational curves. How does that work? Well, this is a refinement of what I did with Junli, and which the rough idea or the philosophy that something like this might be possible goes back to this article of Bogomolov, Hassett, and Chinkel. So how does it work? The idea is that you start from your curve C, and then you can, then you can look at the moduli space of say, so you, without, let's say we have a polarized family, curly X over this disk, and then it sits inside some moduli space, and then there is a Noether-Lefschetz divisor along which the class of C, the line bundle O of C, extends. This may or may not hit the generic fiber, say not, because we can deal with the other case already. So you can move around the rational curve. Now, if you know that, I mean, if you move around the curve C, and you meet on the way a K-free surface which contains C, and in the ample class, which we have as an auxiliary construction, a nodal rational curve, then the point is that you can do the following. You can take C, you can add some auxiliary rational curves so that you land in the line bundle that extends to the generic fiber of curly X. And then you can try to build a stable map out of these bunch of rational curves. This will be a stable map of genus G because it's this given curve C plus some rational curves. Now the problem is, whoever has worked with stable maps knows we have a problem with dimension estimates in the case where we have multiple covers. That is, if you have some multiplicity, so you have, like, for example, the curve C plus 2 times a rational curve, then this, because there is a 2, this can screw up the nice behavior of the Kontsevich moduli space that you have. Now, the idea of this article with Junli was that if you add nodal rational curves, that looks like making it more complicated, you can unwind this situation and construct a stable map out of this, which is rigid. And then you can use the previous result of Rahn, Bloch, and Voisin to push around the genus G stable map. And so this is what is called regeneration. As I said, it is a technique to get from a rational curves in a special fiber to lift to the generic fiber. Now, if you have this, then you can also understand what happens. If you believe this, then you get a very short proof of what I did with Junli. Namely, well, you need a mixed characteristic version of that, and then you have to assume that the special fiber is not uni-ruled. But this you can achieve. And so if you are over a number field, for example, if you have a K-free of odd Picard rank, then you can spread it out. And if it's not defined over a number field, then if you spread it out, you can always find specializations where the Picard rank jumps. Then you can use Bogomolov, Mumford, Mori, Mukai on these specializations. You can find infinitely many specializations that contain loads of new rational curves. And with regeneration, you can cook up new rational curves that you can move back to the generic fiber. And then by a boundedness argument, you can show that the degree with the intersection number of these rational curves you produce this way has to go to infinity. This is, in a very short way, how you prove it for K-free surfaces which are not defined over number fields. In the number field case, and in the odd Picard rank case, you use the fact that over a finite field, or the algebraic closure of a finite field, a K-free surface always has even Picard rank. This is a weird consequence of the Weil conjectures and the Tate conjecture. And so you have a K-free of odd Picard rank, you specialize it infinitely many times, and you every time the Picard rank jumps, and so you produce rational curves you use rational curves in characteristic P, and using regeneration, you bring it to the generic fiber back to characteristic 0. So if you think about this, this is a little bit weird because it somehow doesn't really explain to you where the rational curves come from. They come from characteristic P. But this is enough to, this regeneration technique explains why you have infinitely many rational curves on K-free surfaces of odd Picard rank. You use this Picard jumping and some phenomenon of K-frees over FP bar over the algebraic closure of a finite field. So, so we have a specialization, we have deformation, and we have regeneration. That is this. However, this still isn't enough to treat the rank 2 and rank 4 cases, which are missing. So let me recall again the problem we had. If you have a rational curve on the generic fiber of a family and you specialize it, it might split up. Incidentally, some of you may know that there are formulae that count the number of rational curves on K-free surfaces. There is some quasi-modular form and so forth. And you might wonder, maybe they give you what you want. The answer is no. It could be, in theory, that you have a K-free that only contains a finite number of rational curves, 2000. And then you have all sorts of combinations, just some Ni, Ci. The Ci are the finite number of rational curves. The Ni's goes to infinity. And it could be that the thing that you are counting, you're also counting these multiple rational curves, these non-reduced and not even irreducible rational curves. And if you look at these formulae, this doesn't help you. And so, yeah. So you specialize to a union of rational curves. And now the question is there a way, at least in nice cases, where you have a controlled specialization? Can you have a result like you have a rational curve on the generic fiber of a K-free, you specialize it, and if you assume something, and I will come to that something in a second, you can make sure that the specialization remains integral. It neither becomes reducible nor a sum of something or non-reduced. It stays an integral rational curve. And to explain that, let me mention again moduli spaces. Maybe not. So yeah, this is what I said. This is what we want to do. We want to specialize rational curves to integral rational curves. And to do so, we now need again to work with lattice polarized K-free surfaces. So I will fix a lattice over the integers of finite rank, and I will look at the moduli space of so-called ample lambda polarized K-free surfaces. That means you look at K-free surfaces such that lambda is contained in the Picard group of that K-free surface, primitively contained, and lambda itself contains an ample class. And I will also assume that whenever I write m lambda here, I want to assume that lambda is in fact, that this moduli space is non-empty. Of course, there are various restrictions. If you look, for example, at work of Dolgashev, Nikulin, and others, not every lattice can, of course, arise as a lattice as the Picard lattice of a K-free surface. So, for example, it must be well, there are various constraints. I mean, for example, I mean, it can be at most 20 over the complex numbers, the rank. And what Dolgashev showed is, well, at least this is the only reference I know, has this paper on Arnold's strange duality and mirror symmetry for K-free surfaces. Well, the dimension of this moduli space is, if non-empty, is 20 minus the rank. It is smooth. I mean, as a delinear Mumford stack. I mean, there can be some issue with stabilizers. So otherwise, it's an orbifold. And if the rank isn't too large, maybe this isn't the best estimate, then it's even irreducible. So for example, in especially the ranks we're interested in, namely 2 and 4 for the conjecture, we will talk about an irreducible moduli space. So we have this moduli space of these lambda polarized K-free surfaces. And now what you do is the following statement. Suppose the rank is at least 2, fix a primitive class in that lattice, and assume that we know that for a general point inside this moduli space, assume for simplicity the moduli space is irreducible, that for a general point, there exists a rational curve, an integral rational curve in the linear system associated to this primitive class. Then what we're saying is that if you take a surface inside this moduli space, possibly not general, but such that I mean, M lambda is to be defined that lambda is contained primitively in the pk, such that the lambda is, I mean, that pk is in fact isomorphic to this lambda, then we claim there exists a rational curve in this linear system. So if you, I mean, the idea is essentially that if you have a rational curve on the generic one, and you have another one where the pk lattice is equal to lambda, then you can bring down some rational curve in a way to this surface y, such that it doesn't break up or becomes I mean, of course it cannot become non-reducible because it's primitive. It cannot become multiple, but it could become reducible. It could be a sum of 20 curves or something. And so now the question is, now we are, and so this is basically the contents of one of the papers. And the other paper which we've written is essentially to verify that for the remaining lattices we need to establish the conjecture, that for these lattices that show up there, the assumption that assume that for a general point there exists a rational curve is always fulfilled. So if you look at the moduli space of ample lambda polarized K-free surfaces, we now assume that we have a sufficiently ample class. Sufficiently ample means it's at least the sum of the 3 ample classes. And then Shi Chen already showed 1999 that if lambda is of rank 1, so if we look at classically polarized K-free surfaces, then in sufficiently ample classes, there are always rational curves. This is how he established actually infinitely many rational curves in the very general case. And somehow what we now showed is that this is also true in rank 2 and in various cases in rank 4, namely the missing ones from the earlier from the list. So the upshot of all this is the conjecture on the existence of infinitely many rational curves is true. In the very general case, it is true for odd pk rank, as I mentioned earlier. It is true in pk rank at least 5. There is a finite list of rank 4 lattices, and it's open in rank 2. This can be treated by combining the marked point trick with the existence result from before. And so if you combine all that, the upshot is that every K-free surface contains infinitely many rational curves. So as you see, of course, you're most welcome to come up with a more elegant proof. I mean, usually you would like to have a very good, like a structure or conceptual explanation why this conjecture is true. What we do instead is we show it's true in the very general case, in rather special cases, and we treat the intermediate cases. At least if I can, I will comment also a little bit on the proof of the marked point trick. Somehow, what is interesting is that maybe it doesn't look like that, but the marked point trick is at least something what people might expect or hope why this might be the correct approach to proving the conjecture. We have rank 1 already by these combined results of Bogomolov, Hassett-Schinkel, and Jin Lee and myself. So the hope was that the conjecture becomes easier to prove in higher Picard rank because there's more freedom to play with. And what the marked point trick says is that, well, if you look at lambda polarized K-free surfaces, and you know that what you want to show, namely existence of integral rational curves in some given line bundles, is true in a very general case, then it is true in any given case of the same Picard rank. So, and results like the one in the middle, that given for a very general K-free of inside some moduli space, a result is true. Well, there are techniques for that. There you can look at the moduli space, you can go to the boundary, you can hope that you can find a degeneration into unions of Del Pezzo surfaces or something where you can produce rational curves and then bring back the rational curves from the boundary. I should also say a word why it is called the marked point trick. It is called the marked point trick because somehow the idea is that if you look at the statement, maybe I should, let's see whether this works. So you have your moduli space of, yeah, this works, of lambda polarized K-frees, and it sits inside a moduli space of, you look at the moduli space of rank 1 polarized K-frees, of polarized K-frees. Let's assume for a second, just to make things easier, ample, and let me assume that rank is actually equal to 2, just to simplify things a little bit. And then the idea is that if you have, so on a generic point here, you may assume that that what you want to show is true, namely for a general point, you can find a rational curve. And then what you do is you look at, you push around this rational curve over the whole M of 2D. And then what you do is you mark it with 4 points. So this gives you a map to the moduli space of genus 0 curves with 4 points marked. So this is essentially an affine line. And what happens is that if the point where things break up is where your rational curve can possibly split into a union of something. This will, because if you look at P1, the compactification of this M04, you look at the classifying map to this, and the compactification, which is P1. Then the point where things sort of start degenerating is a point here, but this is an ample divisor on P1. And this implies that the locus where the rational curve will break up will be a divisor inside this whole picture here, inside this circle here. Now, this divisor cannot lie, and then if you set it up correctly, so then the idea is that this divisor that you produce there, the potential problematic point, it cannot go like this. It cannot be sort of, if this It must lie inside this m lambda. And I know I'm desperately vague here. I just wanted to say why it's called marked point trick. The idea is to use a map to M4 bar and M04 bar, use this ampleness or at least something, so that you see that there is a horrible locus where things break up. And then you set the machinery up in such a nice way that this cannot happen at the surface where you're starting from. And this is ensured by this condition here, because somehow if it had to split up, there would be more classes, and you would either sit inside M lambda and be of rank inside M2D, where Picard rank is generically 1. So you get various contradictions. So I should say this is a rather technical result. And if there are questions, maybe I can answer them later. But it is, if you want, a controlled degeneration. So let me mention that there is one more application of this technique. Namely, we can do the following. We are not bound to rational curves. We can also move around curves of higher genus. This has to do with regeneration. Namely, what we can show, of course, I'm not sure whether this was ever a conjecture or whether people were interested in it, but we can just prove it on the way. So if you have a complex projective K-free surface, you can ask, does there exist a curve of an integral curve of genus G bigger or equal than 1 on it? Well, if you have one, then it starts moving inside its linear system usually. So you will always have infinitely many. But you can still ask, do you have like honestly infinitely many curves of genus G in the following sense? Namely, you start with a complex projective K-free, you fix an integer bigger or equal to 1 and an ample class. And then we claim that there exists a sequence of curves of genus G such that the intersection number with this fixed class goes to infinity. So saying that they lie in different linear systems. So it also shows that there are loads and loads of curves of genus G. There was a follow-up article, I wasn't involved there, of Shi Chen and Frank Cornelis, where they studied the question to what extent these curves are moduli complete. So whether you can basically get all curves of genus G on a K-free. But you may have to ask maybe Shi Chen or Frank Cornelis for that. So what this now, the upshot is we have infinitely many rational curves, and we even have infinitely many curves of integral curves of arbitrary geometric genus, and infinitely in the sense here like this one. That, I mean, not just inside some linear system, but really beyond that. Yeah. I think I'm finished already, and yeah, if you have questions, please feel free to ask.
Okay, let's thanks Christian. Yeah. And now questions.
Can I ask a question?
Definitely.
So let's say we have a projective K3 surface and embedded in some projective space.
Mm-hmm.
And let's say the minimum degree of this rational curve it contains in K3 is D. Mm-hmm. It's true that for each degree, like degree D, 2D, 3D, etc., and for each this possible degree, there is a rational curve of this degree.
It is known that if you fix the degree, then there is only finitely many. And so, yeah, well, if you fix the degree, then of course, like as you said, you have, as long as you're effective, then you have this result of the ancient result of where is it? Of Bogomolov, Mumford, Mori, and Mukai, right? which tells you that, for example, if you fix the degree and you just find a line bundle of that degree that is effective, and in your situation you have an embedding already, you have an ample line bundle that restricts to something, so it will be effective. So what this tells you is that you can find a sum of rational curves with every given degree, I guess. But then you run into this business that it could happen that, like, for example, you have a quartic K3. So you have O of 1, and there will be some rational curves, of course. You don't have necessarily lines on a generic quartic. You could have, but you don't necessarily have. Of course, it means that there is, because if you have O of 1, which is ample and effective because it divides the embedding into P3, it means that there is something like a sum of rational curves of degree 4. But I don't think there is any way to say whether you can actually find an irreducible one of rational 4. Think about degree 1. That would be like a line. It can exist, but it doesn't have to exist. Does it answer your question?
Yes. So what I mean is that if we assume this degree D curve is a minimum degree that exists in this K3 surface, and we know that for each multiple of this degree, there exists a rational curve.
So for multiples of this minimal one.
Yes.
I'm not sure, and this is precisely one of the problems of this business. I mean, there is loads of things you can play with, deformations and degenerations, but ensuring integrality is hard. So I'm not sure whether you can say actually something precisely like what you're asking. I mean, you can give partial results, but I'm not sure whether you can say, like, for example, take the quartic in P3, you can find a rational curve of degree 4, and maybe this is the minimal possible because the K3 surface has Picard rank 1 generated by this. Mm-hmm. So of course you have this minimal rational curve, and if you have this primitive generator of the Picard, then in H there is a rational curve, and it's the minimal one that you say. But already for 2H, I have no idea how you can say that there is a new integral rational curve, or whether all rational curves in 2H are merely linear combinations of the rational curves that are already in H.
I see. Thank you.
Christian, maybe I misunderstood this question, but for example, for your example with quartic, if there's quartics which contains lines and doesn't contain spinors.
Oh, yes, but I said that assume that, for example, the Picard rank is 1. Yeah. And assume that, I'm not talking about the very general one.
Well, no, I mean the question, I thought the question was, if you have a minimal degree, then is it true that all the multiple of this degree?
No. The question, you mean minimal degree 1, for example, if you have a line, for example.
Yeah, then two is not there sometimes.
Yeah, okay. Yeah, and if you have a line, for example, on your quartic, then it already tells you that the Picard rank is at least 2, because you have you have a -2 curve and you have this ample class. And then already it's not clear to me whether, if you have linear combinations of that, for example, the class of the line bundle itself is a -2 curve, and multiples of that, there is just the multiple of that rational curve, because this will not become more effective. There's only this one section. So but thank you for these questions. These are precisely the problems where things become complicated.
Christian, I have a small question. So you mentioned briefly about curves of autogenous. So is it true that if you have given K3 surface, that it contains basically all curves?
Yeah, I think this is true, but I think you have to ask Xi Chen and Franco Nelas for what they prove precisely. Okay. So for example, it is well known that I mentioned already elliptic K3 surfaces. But if you just ask for, do you have a genus 1? Do you allow an elliptic curve and then you make it more singular? Then it is well known that, for example, every K3 surface is sort of covered by elliptic curves. They do not necessarily lie in a fibration, but they move around. And they usually, I mean, I think they always have non-trivial moduli, so because of that, you find all of them on it. But of course, all these results, I mean, it's hard to actually explicitly find these curves. Yeah.
Thank you. And more questions to Christian?
Well,
This is like sort of, go on.
Go ahead.
Hello, can I ask, so maybe I missed this, but what in characteristic P, what is the situation? Is it an open question or
yes,
is it known?
Yes, yes. I didn't say anything about this, but because the situation there is a little bit more complicated. We have infinitely many rational curves now in characteristic P bigger or equal to 5. This we have. The problem, what is missing, is it's a tiny step in small characteristics. And it's slightly embarrassing to say this because it is, where is it? It's this here. Bogomolov and Schinkel proved that there is infinitely many rational curves on an elliptic K-free. And this requires an analysis of the, there's the monodromy representation. If you look at this fibration, you look at the monodromy representation of the generic fiber. And there are some subtle arguments. This has been dealt with by Salim Tayyou recently. And there are a couple of cases in characteristic 2 and 3 where he hasn't achieved this. So we have infinitely many rational curves, at least in characteristic at least 5. And then another thing, so for rational curves, this is the situation. And here in character and for this result, we have partial results for G equals 1, for genus 1 curves on K-frees. The problem is higher genus, and this is a slightly embarrassing thing. What you need at some point, and this is essentially over the complex numbers, I think this is a result of Cornalba, Arbarello, Griffith, and Harris, that if you have a genus G curve on a K-free, then the expected dimension on how it moves on a K-free is G. So you would expect a rational curve to be rigid. You would expect a genus 1 curve to move in a one-dimensional system. Now, for rational curves, if a rational curve is not rigid, this can happen in characteristic P, and then it means that the surface in question is uniruled, supersingular, and so forth. But what does it mean for a K-free surface, for example, to contain a genus 2 curve which moves in a 3-dimensional family? I mean, where you have a 3-dimensional family, what does it mean? We don't know whether this, I mean, in characteristic 0, there is a result which uses rather subtle differential invariance. However, in characteristic P, the proof breaks down, and we don't know. I mean, what would it mean that a K-free is sort of covered by too many curves of genus 3? Could happen. We don't see anything why it couldn't happen. We know it may happen for genus 0, like there are unirational K-frees. So we don't know. So the upshot is the result on infinitely many rational curves is true in characteristic at least 5, with the small exceptions, and with some small exceptions where we don't know it in characteristic 2 and 3. We were hoping for Salim Tayyou to improve on his result there. And we know we have this more general result here for arbitrary genus, at least in genus 1, I think, but we don't know in higher genus.
Thank you, Christian.
Okay.
More questions?
Yeah, I was going to ask, this is a totally different question, but what about, you know, density of rational curves in the classical topology? I think something is known here.
Say it again, about density of rational curves, or
In the classical topology, you know, I mean, I think some people have studied that.
Yeah, I think we cannot say anything about that, because basically to be honest, we haven't thought about that. But my gut feeling would say that the kind of techniques we're using, this sort of degeneration, I mean, I wouldn't know how you can, maybe you can say something in the generic case. I'm not sure. No, let me be honest, I don't know. And we haven't thought about this.
Thanks.
More questions? I have small question. What about the say number fields or non-closed fields?
Yeah. Again, we do not know. The problem is, again, the techniques we have is what you usually do is, for example, in this regeneration trick, you start moving around the curve, and then you add rational curves. You add nodal rational curves. And we know that they are there sort of over the algebraic closure of I mean, geometrically, but we have no idea about the fields of definition. So the answer is we don't know, because also, and the techniques don't give that.
Okay, thank you. Actually, Bogomolov, I think.
I see that
Jenny found the link. Yeah.
Great. Yeah. So I don't know. I mean, this other paper about the moduli completeness. There is something, but I don't know precisely what they did.
Okay. If there are no more questions to Christian, let's thank him again for beautiful talk. Yeah, thank you very much. And thanks everyone for participating in the ZAC seminar. Despite the fact that semester already started in many universities, everyone is busy. Thank you very much. And see you next week. Bye. I will upload the video soon today.
Thank you.
Thanks. Bye. Bye.
Bye.